So, the band pass filter's transfer function is S over what do we call it, omega naught, omega p? Okay. So, p divided by S square by omega p square plus S over omega p qp plus 1 gain or mod h of j omega p, which is the magnitude response at omega p, is 1, and the 3 dB bandwidth turns out to be omega p over q. So, as qp keeps increasing, the bandwidth of the band pass filter keeps reducing. Okay. Now, the high pass filter's response is basically S square by omega p square over 1 plus S over plus S square over omega p square. So, as S tends to 0, what is the response? 0. As S tends to infinity, yeah, at large frequency, basically this numerator is S square by omega p square, and these two terms will be very small compared to that term. So, basically mod as S tends to infinity, this tends to 1. Clear? Okay. So, now the next thing is and again you can go and do the math and find that, you know, for qp equal to, for the special case of qp being equal to 1 by root 2, right, you will basically end up with a maximally flat response, just like in the low pass filter case. Okay. So, I mean, you can basically think of this as simply, I mean, you can see that this is now, if you write down the magnitude response, square of the magnitude response, is nothing but omega square by omega p square over 1 minus omega square. So, this is whole square actually, 1 minus omega square by omega p square, the whole square, plus omega square over omega p square qp square. Correct? Oh, sorry. Okay. Now, which I will divide the numerator and denominator by multiply the numerator and denominator by omega p to the power 4 by omega to the power 4, and then what will I get? I will get omega p square by omega square minus 1 whole square plus omega p square by omega square times qp square. Okay. And if you recall, this was exactly similar to this, except that this is 1 minus omega square by omega p square the whole square plus omega square over omega p square qp square. So, you take the low pass response, replace omega by omega p with omega p by, and you will get the high pass. So, whatever happens at DC in the low pass, at DC omega by omega p is 0, omega p by omega is infinity. So, whatever will happen here at DC will happen here at infinite frequency. Okay. And whatever happens at omega by omega p equal to 1 will happen there at omega p equal to 1, right. So, in the special case of in the special case of qp equal to 1 by root 2, the low pass filter had a Butterworth response and its magnitude response was 1 over root 2. Similarly, the high pass filter will also have a response which is 1 over root 2. The low pass response will be maximally flat at DC and start falling off like this. The high pass response will be maximally flat at infinity and will fall off, when it goes towards DC, it drops down to 1 by root 2 at omega equal to omega. Okay. So, now let us start looking at the passive networks like we did. Remember that the low pass filter transfer function we want to realize is of the form 1 over 1 plus s by omega p q p plus s square over omega p square. So, the first order, to get a first order RC low pass, low pass filter, we basically put R and C here. So, this is Vi and this is Vo. At high frequency, this impedance becomes, so recall, first order low pass filter, the transfer function is 1 by 1 plus s by omega naught. As at infinite frequency, as frequency tends to infinity, what comment can you make about this response? How does this go asymptotically? Which at infinite frequency it goes to 0, right, but at large frequency, which term in the denominator dominates? S by omega naught. So, the transfer function approximately is omega naught over s. Okay. And in the network, what is happening at very high frequency? What comment can you make about this voltage? The capacitor acts like a short circuit, so the that voltage is very small. So, what comment can you make about this current? This is at high frequency, this current is approximately Vi by R. What is this? That current flows into this impedance. What is the impedance at high frequency? What is the impedance of the capacitor? 1 by SC. So, what is the voltage? So, current V by R flows through an impedance of value 1 by SC. So, what comment can you make about the voltage at high frequency? Vi by R flows into a impedance of 1 by SC. So, basically the output voltage at high frequency is approximately Vi by SCR, and so therefore, it is clear that what must omega naught be? 1 by RC. Okay. All right. Now, let us say now we want, so here at high frequency, so at high frequency basically this the voltage across the capacitor is 0 or very small. So, basically current that flows through the resistor is approximately Vi by R. That is the current that flows through the capacitive impedance of 1 over SC. So, at high frequency, therefore, we should expect the output to go as 1 over as Vi over R times SC. Does that make sense? Now, let us say we want at high frequency as S tends to infinity, the second order low pass filter transfer function tends to goes as omega p square over S square, and if we want to basically create a network which does this. So, let us say we have some impedance here Z, this is C, correct, and at this is Vi. So, at very high frequency we expect that the voltage across the capacitor is very small, right. So, this current must be Vi by Z, and therefore, at high frequency the voltage Vo of S must be Vi by Z of S, must tend to must basically go as Vi by Z of S times 1 over SC, and that must be Vi times omega p square over S square, correct. So, what must we have in Z of S as S tends to infinity? Z of S must go as Z of S times SC must be equal to S square over omega p square. So, therefore, Z of S as S tends to infinity must be go as S over omega p square times C. So, what impedance can you think of? And at DC, the capacitor must be, the capacitor is open, right, and what must the impedance here must be, what must be the DC impedance of Z? I mean, even it does not matter whether it is 0 or it is a constant, it is a non-zero constant, correct, because no current is flowing through it. The only thing is it cannot be infinite at DC, correct. So, as S tends to 0, the Z of S must tend to some constant, let us call that R, right. As S tends to infinity, Z of S must tend to infinity. So, can you think of a simple element, simple impedance where the resistance at DC, the impedance at DC is some resistance, and as the frequency tends to infinity, the impedance also tends to infinity. R in series with inductor, right. So, this is Vo, this is Vi, right. As S now you can actually find the transfer function. So, Vo by Vi is nothing but 1 over SC over 1 over SC plus SL plus R, which is basically 1 over S square LC plus SCR plus 1. So, and this we said is going to be of the form 1 over S square by omega p square plus S over omega p q p plus 1. So, omega p square is nothing but 1 by L C, which means omega p is 1 by under root L times C, and omega p q p is therefore um, uh, 1 by square root L C times q p, and that is nothing but C times R. Okay, never mind. So, q p therefore is sorry omega q p, yeah, sorry, 1 by R C. So, what is q p? 1 over R square root of L by C. Okay. So, so looking at this network, this realizes a second order low pass filter with omega p is 1 by square root L C, and q p is 1 by R square root of L by C. Okay. All right. So, this is what this is what so I mean as I mean as a sanity check, at high frequency, what is the current that flows there? Which impedance, R or L, dominates at high frequency? Inductor. So, the what, and at high frequency the capacitor is short. So, what comment can we make about the current flowing through the RL branch at high frequency? Vi by SL, approximately Vi by SL, and therefore the voltage at high frequency is going to be Vi by SL times 1 over SC. So, this is basically Vi over S square LC, and this must be equal to Vi over times omega p square by S square, correct. So, omega p is equal to 1 by square root L C, and that makes sense because we have also done it by finding the writing the whole long expression. Is that clear? All right. So, now the question is, and again this has the same problems as we had with the first order network. You put a load, then what happens? Basically, not only does omega naught change, it turns out that q will also change, and on top of it the DC gain will also change, right. So, this is a problem. So, and besides, what happens is that I mean, so let us say you are trying to realize a filter. Let us say example, so let us say omega naught is 2 pi into 20 kilohertz. So, which is approximately 120 into 10 power 3 radian per second, right. And let us say we are trying to build a maximally flat filter. So, QP is 1 by root 2. Okay. And let us say we choose say R is equal to 50 kilo ohm, right. So, what should and let us say C is say 1 nanofarad. Okay. So, can you calculate L? what is it? What answer did you get? Yes. Okay. Into 10 power. Wait. Huh? Oh, okay, fine. So basically, so if you choose C, if you choose C equal to, so you can't choose both at obviously at the same time. So if you choose C is 1 nanofarad, L is 0.1 Henry, and what should R be? Okay. So you can see that if you want to design for example, a low frequency filter like the one here, which is a second order filter, which is intended to cut off frequencies beyond audio, right? Then you see that the 1 nanofarad is actually quite a large capacitor, and the inductance needed is 0.1 Henries. Okay, and 0.1 Henries turns out to get 0.1 Henries is actually very difficult. The inductor is going to be very bulky, right? Okay, so it's impractical. So with respect to second order filters, we have yet another problem, namely that the component, the value needed for the inductor is very